Yes, so this is joint work with my colleagues Lexi Brent, Lagovardos, Bernard Scholz, and Yaris Margagis. Most of us have moved on from academia to industry since the time this paper was written. And also, as the previous author suggested, smart contracts have changed quite a bit since 2020, since this paper was written. I'll tell you at the end of the presentation how we kind of evolved this work further, but I'll start by giving you an introduction to the space. So the space of smart contract vulnerability is almost as old as smart contracts themselves. In fact, the very first vulnerability, called the reentrancy hack, happened in 2016, which is 1 year after the network was deployed. The Ethereum network was deployed in 2015. Now, this is how this happened. So the hacker deployed a smart contract and also deposited some funds in a victim smart contract. It was called the DAO back then. What happened is that as soon as the hacker smart contract got executed, the withdraw function, it called the withdraw function in the victim smart contract, and it got some of its funds back. Now, one of the quirks with blockchain smart contracts is that transferring of funds is normally associated with calling a function. And so the withdraw function, in addition to sending the funds, it also called a function on the hacker smart contracts, but the hacker smart contract called back the victim smart contracts, which meant that the withdraw function didn't exit, it was still running. It re-entered. And so this created a cascade of withdrawals. And in the meantime, the balance was not updated. And this slowly drained the entire balance of the DAO smart contract. So that was around $60 million in total. And what happened after this is that there was a cascade of research in smart contract security tooling, either static analysis or formal verification. And in fact, in 2017, people started writing smart contract analysis tools. But these tools were mainly designed to capture single transaction issues. So issues that happen within a single invocation of a smart contract. Here's an example of one of these single invocation issues here. Now, I'm going to use the analogy of pirates, rooms, gold, where the pirate is the hacker, and the objective of the pirate is to steal the gold from the smart contract. That is the room that you see here. Luckily for the pirate, there's a door in the room and it's open. This translates in code to the analogy on the left-hand side. We can see a function kill, which has a public qualifier. Anyone can call the smart contract, and there's no condition within the body of that function which checks whether what the user who's calling that smart contract is. And so then the self-destruct function is called, and the hacker can pass their own address as a beneficiary. And what self-destruct does is it removes the code of the smart contract and its state, and also transfers all the remaining funds to the hacker. This kind of vulnerability is called an accessible self-destruct. It's one of the main vulnerabilities that Ethainter finds. Obviously, this is a very simple example, but I'm going to show you more complicated ones. In fact, in that same year, 2017, there was an even larger vulnerability that happened. So this one was on the parity smart contract. And in fact, even back then, this vulnerability required multiple invocation of the smart contract. As we can see, here's an interaction between the hacker and the community on GitHub. And the community was blaming the hacker that it was not something which was done accidentally, because it required two invocations of the smart contract. One to reinitialize the smart contract with the hacker being the owner of the smart contract, and one to kill the smart contract itself. Okay, so even back then, vulnerabilities were started to become more and more sophisticated. And so within the Solidity smart contract language, there are constructs. These are called modifiers and are usually used to protect, for instance, a function from being called by any user. So here's an example. The analogy here is that we still have a room and it still has a door, but the door is locked. The lock is protected by this modifier here, requiring that message sender, which is the caller of the smart contract, to be a specific user. But unfortunately, especially, like within 2020, there were lots of tools which still didn't have any reasoning about this sort of logic. And so they could mark these smart contracts as being vulnerable. Now, Ethainter finds composite vulnerabilities, meaning that even if there's a lock, even if there's, for instance, here in the kill function, we are checking that message sender is a particular user, despite that, taint could travel to that particular location in storage, the owner there. So in the analogy, if we have a key which is placed in a room which is unlocked, that can be used to unlock the locked room. Okay? So the hacker simply has to set themselves as the owner and then call the kill function. So that would capture the previous vulnerability that I showed you. This kind of vulnerability is called tainted owner variable. Now, Ethainter uses sound program analysis principles, which means that we can apply this logic recursively. And the key message here is that you shouldn't just look at locks in doors, the analogy being that you shouldn't just look at code which is protected by modifiers, but if these modifiers, their predicates can be tainted and so on and so forth transitively, then they are also vulnerable. Okay, now let's look at another example. This one is slightly different. In this example, we have a trusted user. These are usually referred to as keepers. Okay, they could also be administrators, but especially in decentralized finance smart contracts, we have bots which typically call a smart contract every few hours to do a particular centralized activity, maybe transferring funds periodically or rebalancing pools, things like that. Okay, so these users are not actually sentient, and they will just keep calling the smart contract over and over again. So in this example, we still have a locked room, and there is no way in which the key to the locked room can be modified or can be taken. However, there's another room which has an open door, and it contains the address of the beneficiary. So what the hacker can do is can set themselves as the beneficiary, and when the keeper loads that information, it uses that information to transfer the gold to the hacker. Now, on the analogy on the left-hand side, the code is shows a similar story. We have the set beneficiary where we can set ourselves, that is message.sender, as being the beneficiary, and when the unsuspecting keeper calls the harvest function, okay, it will send all the remaining funds to the beneficiary. Now, this kind of vulnerability is called tainted self-destruct. Right, now, let's get to the semantics. So the bottom part of the slide discusses the format of our rules. Let's start from a simple rule. This rule says that any user input taints the variable to which that user input flows to directly. Now, notice that we have two kinds of taints. We have taint from input and taint from storage. Why is that? Well, taint from input can flow through transient parts of the Ethereum virtual machine. So that would be like stack variables or memory. Whereas taint from input can flow untrammeled, taint from storage can flow untrammeled throughout multiple transactions. And so we need to take into consideration not just the data flow within a single function, but also across multiple transactions. So now these two rules here, for instance, operation 1 talks about taint flowing through operands on operations. Now, these rules over here, guard 1, say that if a variable is tainted from storage, then it can flow untrammeled through a guard. And in the case of guard 2, this says that if the guard predicate, so that's the condition which is used by a guard, fails to sanitize, most likely because there's been taint which has traveled to that predicate, then if that guard fails to sanitize, then taint can travel untrammeled through that guard as well. We have another set of rules here. These ones deal with storage. Okay, so the first rule says that if we have a storage location and we are storing something to the storage location, then, and that something is tainted, then the storage location is also tainted. Now, the dual of that rule is storage load, meaning that when we load something from storage and that storage location is tainted, then the variable we're loading it into is also tainted as well. These final two rules are perhaps the most interesting, and these ones say that if we have a guard predicate and there's taint that travels to that predicate, one of these variables, for instance, z, okay, and that storage location is tainted, then that guard will fail to sanitize, that predicate will fail to sanitize, which means that then taint can travel through the guard. And then we have another rule saying that if we have a guard, but it doesn't index the message.sender, then that also fails to sanitize. Okay, it's guarding against something else, not user access. Now let's see how this has been implemented in Datalog. Now for Datalog, we didn't do a one-to-one translation from semantics to Datalog rules. Instead, the Datalog rules were written in a way as to be scalable, but at the same time, they also are faithful to the specification. For instance, we have a rule here which says, first of all, there's a relation attacker model info flow, which says that a variable, for instance, y, can flow to z. But this is not a transitive rule. So we can apply it transitively like this to form a transitive closure. And so we do a transitive closure in a similar way to data flow analysis. Now, this might not be surprising so far, because taint analysis is similar to data flow analysis. What is perhaps more interesting is that this implementation borrows ideas from pointer analysis with on-the-fly call graph construction. Now, where would on-the-fly call graph construction fit into this? After all, we've already done call graph construction before we do a taint analysis of the program. Here's the interesting part. We have a relation reachable by attacker, which says that a statement can be reachable by an attacker even if that statement is statically guarded by a guard, meaning that the attacker normally cannot reach that, under static conditions. But if there is taint that flows to that guard predicate, then that part is also reachable by the attacker. Okay? Likewise, any statement which is not statically guarded can also be reached by the attacker. Okay, so this has a similar structure to on-the-fly call graph construction, but it's not used for call graph construction. Okay, and the performance of this analysis is pretty good. Okay, so let's start looking at the results. So we've implemented Ethainter in the data log language, and it borrows the underlying framework, which is the GigaHorse toolchain, in order to first decompile the smart contracts from bytecode to a tree-address IR representation, which is amenable to analysis, and then applies the analysis on this representation. Because the underlying framework is pretty scalable, we inherited that scalability in Ethainter as well. And we've applied Ethainter to all the smart contracts that we could extract from the blockchain at that point in time. So that's 262,000 smart contracts at that point in time. And we can see that the percentages of smart contracts that are flagged for a particular vulnerability are pretty low. Obviously, you wouldn't expect that most smart contracts are vulnerable, but they're also pretty realistic, especially, for instance, accessible self-destruct, which, in order to verify that the vulnerabilities that we are flagging are true, what we did is we implemented another tool which tries, using some heuristics, to actually destroy the smart contracts that were flagged. Now, this tool is not perfect. It has like a couple of heuristics, and it will obviously not find very smart ways to actually execute hacks. But on the Ropsten test network, which is not a live network, it's something which is used by developers to test their own implementations, we were able to destroy 805 smart contracts that were flagged. So that means a 17% success rate. Okay. All right. Now, we've also tested Ethainter against other tools which perform similar analysis. One of them was the Securify tool, which has since been updated. I'll show that in the next slide, and then abandoned after that. But what we did in this case, in order to analyze the precision, is we picked 50 smart contracts that were flagged by one tool, that is Ethainter, and 50 smart contracts flagged by Securify. And then we spent, say, 30 minutes on every smart contract that was flagged to figure out that whether the vulnerability is a false positive or not. In order to make the process even more easier for us, we only limited ourselves to smart contracts that had source code. Now, what we found out is that the precision of Ethainter was pretty high, around 80%. However, for that of Securify, it was around 0%. And that was surprising at first. The reason was that Securify actually flags 75% of all the smart contracts that it could run for some violation, okay? And that's exceptionally high. It doesn't mean that 3/4 of all the smart contracts deployed are vulnerable, right? That's unrealistic. Here's an example of one of the smart contracts that was flagged. And in fact, actually, this came up again and again in smart contracts that we saw. In the case of Securify, this is a standard ERC20 token. When you transfer a token, balances are going to change, right? And this is normal. It doesn't mean that the smart contract is vulnerable. We also tested against Securify 2.0, which is a slightly different animal because this is a source code analysis tool. Okay, it has much better precision, But it actually took quite a bit of work to do this experiment because it's not exactly apples to apples. Ours is like bytecode analysis. So there's a limited subset of smart contracts that have source code. At that time, it was like 3% with solidity 0.5.8 and above. Nowadays, there's going to be a lot more because it's been more expensive to deploy smart contracts. And on top of that, the compiler versions have gone up to 0.8. So there's more source code available since 2020. But in any case, we got slightly better precision and also better scalability. But one particular interesting thing that we saw is that the source code analysis frameworks, they miss a lot of vulnerabilities. And that is because the libraries, the low-level libraries which implement standard features in smart contracts, use inline assembly. So for instance, delegate call was implemented, which allows you to use another smart contract's code to perform an operation on your own smart contract. It's not something which was implemented in Solidity, and so they used libraries that implemented this using inline assembly. And so are many other libraries out there which use inline assembly as well. And source code analysis tools don't capture this because inline assembly is almost as low level as bytecode. And yeah, it's might as well just analyze the bytecode, right? Another discussion here is against symbolic execution. So we also tested our approach against Ethainter. Now, Ethainter times out or raises an error on the majority of contracts that we've tried. But I guess the most interesting aspect is that in the case of Ethainter, it only flagged 641 smart contracts versus 2,830, which is flagged by Ethainter. And there's a reason for this. It's because this symbolic execution tool in particular, it only analyzed the simplest flows through a smart contract. Whereas the more interesting flows are the ones that are more likely to have some issue. So an example of an uninteresting flow would be a flow which, you enter a function, you check for an error, you raise an exception. That is an uninteresting flow, right? The reason why it did that is because it didn't scale to these smart contracts. Okay, there's a few other issues we've seen, like when we tried Ethainter against smart contracts that we know that have already been self-destructed, for instance, then the gap between the percentage of contracts that we flagged versus they flagged was around 34 times. Okay, cool. So now I just have one slide to discuss what happened since we originally wrote this paper and now. So this paper was published in 2020, but most of the work was done around 2019. Now, in the DeFi summer of 2020, there were a lot of new applications that were incubated on the blockchain, and these applications were really interesting and also really complicated. Okay. Now, what happened is that even though the access pattern that we checked in Ethainter were effective for smart contracts deployed around 2018, because these smart contracts were, maybe crowd sale smart contracts or ERC20 tokens, so they were quite simple, they became much less effective for modern applications. Modern applications have a lot more conditions that they check for. And so the logic which finds statically guarded parts of the smart contract didn't work as well. Ethainter does not perform symbolic reasoning. And so complex conditions were sometimes confused with guards. And on the other hand, complex guards, things which deal with financial logic, were often not modeled. Okay? So So yeah, on these smart contracts, it's both precise and incomplete. And so what we did is that since then, we've re-implemented Ethainter on top of the symbolic value flow analysis engine, which Yanis presented yesterday in the same room. And this adds symbolic reasoning. And so we are more able to capture the idiomatic conditions that are used in modern smart contracts. Okay, but it required quite a bit of modernization. So in conclusion, Ethainter is a powerful security analysis framework, which is more precise and more complete than alternative approaches that we've seen. It is fully automatic, push button, and analyzes smart contract, scales to the entire blockchain, and recently it was adapted to more modern applications and deployed as part of some of the DOPS products. Thank you.
Great. We have time for a couple of questions.
Can you go to slide 15, like the counter example? So here, like, I think like when the address to equal the address from, you can do transfer without having enough balance. Like the if conditions.
Yeah, so this protects against this, right?
Yes.
Yes?
Yeah, very interesting talk, thank you. So I'm asking a little bit about clarification model measures. So the first one is that when you do analysis, do you like it's a static approach or it's like you have to implementation during runtime?
Right, so it's a completely static approach, the analysis. There was a tool which we implemented which takes the static analysis results and tries to actually execute them. But that was more to like convince ourselves that the results are okay in terms of like precision.
Okay, thank you. The second one is regarding the guards. So which part of the language feature are you taking them as guards? For example, we have requirement statements, which if you violate, you would have to revert, right?
Yes.
And then we also have guarding conditions like if else. So which one are you considering as guards?
Right. So in the case of Ethainter, we were taking any guard which ended up if you have a revert or an assert false, which is like a jump I to a wrong location on in the smart contract, and if that dominates or post dominates the execution, and that's modeled as a guard. And so it takes into consideration require, but also, if, then throw, things like that.
The second question was more regarding the call contract features. So how do you handle that?
The what?
Calls, if the contract calls other contracts, so you let go the other. So how do you handle this?
So if there is a require and you actually call another smart contract to check for a particular condition, then that is not modeled. So then it will miss that.
Thank you.
Okay.
With this symbolic analysis now, we have two levels of confidence, and the high level does not issue a warning if what you pass to the XML call is affected by the message in your call. So like we don't model the other contract, but there's not much one can do without doing that. But that's the follow-up work that never described how this.
So a question I had was involves, so it seemed like you are finding kind of patterns of vulnerabilities, right? And you're incorporating some semantic aspects, but you are basically looking for, as I could see it, you're looking for patterns of particular ways of extracting things out of contracts. Is this the best we can do with smart contract vulnerability analysis, or are there? I guess I'm interested in kind of your retrospective on sort of patterns versus more general kinds of semantic approaches, and where you fall on that spectrum.
Okay, So we fall somewhere in between in that spectrum. There's a few things which are not pattern related. So say, for instance, if we write a taint analysis, it is a general taint analysis which does, taint, information flowing through control flows and things like that with context sensitivity. So there's nothing pattern related with that. Now, we do need to make some design decisions. So say, for instance, certain operations actually transfer entropy through them pretty well, right?
Mhm.
Whereas, maybe operations like hashes, they don't transfer the entropy that well in the case of taint analysis.
Mhm.
So there is a little bit of pattern matching. The other thing is, for instance, with the guards, in the case of statically modeling the guards, which is done before we apply the Ethainter analysis, actually. In that case, that's pattern matched, but it uses, say, for instance, concepts like dominator frontiers and things like that.
Mm.
In the case of the symbolic analysis, which is like a later piece of work, that does more semantic modeling, but it models certain aspects, certain operations better than others
Mhm.
because they're more idiomatically used in smart contracts.
Yeah. Okay. Thank you.
Welcome.
All right. Let's thank Neville again.